Alrighty, so here's a bit of our last bonus lesson for this unit. Suppose we want to work backwards using a percentile to figure out which observation would correspond to a particular location within this normal distribution. We will proceed to use a normal model. However, we will find a particular z-score to correspond to the percentile we're looking for, and we'll use our inverse formula to find the observation. Now, here are some common inverse normal scores. Now, I'm going to teach you how to do it for when it doesn't fall at one of these nice little values on a calculator, but we won't be getting spicy with the calculator till next semester. So we're going to just focus on doing it with the tables, and then of course for the actual AP exam I'll show you how to do it like that. But until then, we got to know where it's coming from. Now I want you to think about this. Every time we deal with normal distributions, there are three components. X, which is the observation. X has a corresponding z-score, which tells me its location relative to the mean. And then each of those z-scores, the probability less than that z-score is a percentile. So there are really three components: the observation, its z-score, and its percentile. So you need to keep that in mind, and something that's very popular on the AP exam is giving you a percentile or giving you a z-score and then having you compare where those values fall in a normal model. Of course, we'll do more practice with this. But for now, let's take a look at these z-scores here. So this says that if I wanted the 30th percentile, my z-score should be at about negative 0.39. So let's go here to negative 0.39. So here's negative 0.39, and it's going to be, you see, about 0.3483. That's about 35% of the data. So 35% of the data is at or below a z-score of negative 0.39. Let's take a look at a different z-score. Oh, that's my recording screen. Let's suppose I wanted the 75th percentile, another popular one. Well, a z-score of about 0.67, so let's go here to positive 0.67. So a z-score here at 0.67 is going to happen at the 0.7486. That's its percentile. Notice if I go one up, that's above 75%. So this is at or less than 75%. So there's a more technical way to do this with the calculator, but for now we're just going to keep it to these very basic problems here where it'll fall on one of these nice z-scores for you. And notice the symmetry of the situation here. So if I want 5% or I want 95%, those would fall around the same place, so notice their z-scores are opposites of one another. Or if I wanted 10% and 90%, 15 and 85, and you can see this symmetry getting closer to the mean and getting above the mean. So here at the mean, a z-score would have 50% of the data has a z-score at 0, because the mean is equal to the median is equal to the mode. So there's just all these connections that can be made with these problems, but enough hoopla. Let's actually talk about solving these problems. So if a distribution of entrance exam scores is normally distributed with a mean of 1800 and a standard deviation of 80, then what student entrance exam score represents the 90th percentile? So again, there it's already giving us the proportion of data. 90% or less happens at this z-score of this observation. So we'll still keep our picture here. So we'll say x is, we'll skip a step, see? X is going to be your score on the entrance exam. So x equals entrance exam score. And I know that x is distributed normally with a mean of 1800 and a, kind of lost power there. Hold on, technical difficulties. I'm going to just quickly pause this video. Why don't you pause and process? Alrighty, sorry about that. Technical difficulties over. So x is the entrance exam score. X is distributed normally. And I want the 90th percentile. So the z-score that corresponds to the 90th percentile, using my tables up here, these are not provided on the AP exam because there's an actual technique to finding them. So for now, I'm just going to give you very nicely done inverse problems. So here at the 90th percentile, we have a z-score of 1.282. So that's going to happen at about here. So that's my z-score of about 1.282. And this area underneath that z-score corresponds to a percentile of 90%. So I need to figure out the observation. And so of course here's 1800, here's 1880, here's 1960, and down here is going to be 1720. I don't know why my pen is not being friendly, and 1640. And I'll leave, I think you can find the other areas by some symmetry there. But I have the percentile, I have the z-score, now I need the observation. So let's think back to the formula we've been using. We've been using this formula here, which says a z-score equals x minus mu over sigma. But there's a way to solve this for x, and we've actually talked about this back in section 1.10 or 1.11, but x also equals mu plus z sigma. So if you solve this equation backwards, you get this for x. And again, because x has a z-score, and that z-score tells me how many, here's where it gets cool, how many standard deviations I am above or below the mean. So that's really what we're interpreting when we're interpreting the z-score. So now to find this x, we're just going to sub in what we know. For example, our mean is 1800, our z-score is 1.282, and our sigma is 80. So guess what? An observation of 1,902.56 points corresponds to a z-score of 1.282, and this is at the 90th percentile. So you can now see the three components there. An observation, its z-score, and the percentile of data that occurs at or below this value. So my statement would just sound like the student entrance exam score that represents the 90th percentile is 1902.56 points. And if you were asked to interpret that, you would say the value of 1902.56 is at the 90th percentile, meaning that 90% of student entrance exam scores are at or below this value. So you see now all the connections that we've been doing in this unit. So that is a lower bound example. So let's do an above example, and there won't be any between examples here. Usually the between is just for the probability. So I want you to try this one out. So pause the video, give me your parameters, shade a picture, and try a solution out here. But we're going to come back because, of course, in true math teacher fashion, there's always a twist. So pause the video and at least get the setup going, and we'll see what happens from here. So go ahead and pause and go. So I'm assuming you paused and at least got this far, and then you ask yourself, wait a second. I want the top 70% of data. So I want the top 70. Who am I ignoring? What's my minimal exam score? Because I don't want the bottom 70. That wasn't what the question was asking. It wants the top 70. So what's my minimal acceptance score there? Well, it's going to be about 30%, right? Because if I want the top 70%, I need to ignore the bottom 30. So let's go ahead and check out where does a 30th percentile occur. So 30th percentile, negative 0.524. Okay, so that should be in between 0 and negative 1, so about right here. So the area to the left will be the bottom 30%, and then the area to the right will be the top 70%. And a z-score for the 30th percentile happens here at negative 0.524. So I need and I know the percentile there is going to be 0.3, but I want the top 70. So I need to find that minimal score for the 30th percentile, and instead of taking everyone below that, I'm going to take everyone above that. So again, this idea of subtracting from 1, you're going to shade to the right instead of shading to the left, and I'm realizing I've mirrored, so right, not left. There we go. All right, so same thing here. We've got our z-score. And we're just going to use our inverse formula where x equals mu plus z sigma. So x will equal a population mean score of 500 plus the z-score of negative 0.524 times the standard deviation of 100. So the score that is the 30th percentile will be 447.6 points. So that's the minimal exam score, or the minimal acceptance score, to be in the top 70% of data. So again, same thing, you want to indicate the use of a normal model, you'll want to show your work, and you'll want to get your final answer. AP exam rubrics are really weird, like it changes each time, but when we are finding probabilities, when we're finding the percentile, we need picture, parameter, probability statement, problem conclusion. When we are finding the inverse percentile and inverse normal calculation, we just need the parameters, we need to show some work, and we need our final answer. So I don't have a cute acronym for that. But you would just restate the question here. The minimal acceptance score to be considered in the top 70% of all scores is 447.6 points there. So you can see, again, this idea. The three things I want you to think about when we're dealing with normal distributions. X, which is the observation. This observation has a z-score on this normal curve, and based on its location, there's a percentile of data that is located at or below this value. So that's going to wrap up the second half of Unit 1, Unit 1b, the normal distribution. We talked about transforming data. We talked about percentiles and z-scores. We talked about the empirical rules / the general normal model and the standard normal model. And now we've actually used the normal model to calculate percentiles. So that's going to conclude our Unit 1, our analysis of univariate data. So in Unit 2, we're going to talk about bivariate data and starting to include two separate quantitative variables and looking at relationships between the two. But for now, we're just going to keep practicing. We're going to get very familiar with the normal distribution, and we're going to crush this 20% of AP exam that is based on Unit 1. So thank you all. Stay tuned for more exciting AP Stats magic. Alrighty. Bye-bye.